So far, we had seen reactions as the transformation of reactants into products that proceed until they are complete, which is until the limiting reactant is used up. This is called a non-reversible or irreversible reaction, which the chemical reaction proceed in only one direction. One of the examples of an irreversible reaction is a combustion. The combustion of carbon in excess oxygen will form a carbon dioxide. This carbon dioxide could not form the carbon and oxygen back. In reversible reactions, the reactants and products are never fully consumed. They are each constantly reacting and being produced. So, the chemical reaction takes place in both forward and reverse direction. When the forward reaction continues and the reverse reaction occurs at the same time, the rate of the forward reaction is equals to the rate of reverse reaction. At this point, there is no further changes appears in the concentration of the reactants and also the products. The reaction quotient is equals to the equilibrium constant and the reaction mixture has reached the dynamic equilibrium. One of the examples of dynamic equilibrium is if you're moving upward on the escalator that is moving downward at the same speed, there is no change in your position. Consider the reversible reaction of the calcium carbonate. This reversible reaction can be broken into the two reactions. The first reaction is involving the decomposition of the calcium carbonate, where it will form the calcium oxide and also the carbon dioxide gas. And the second reaction is involving the formation of the calcium carbonate from the reaction of calcium oxide with the carbon dioxide. In principle, every reaction is reversible and will reach dynamic equilibrium if all the reactants and products are present. When the calcium carbonate is placed in an open container and heated, the calcium carbonate starts breaking down to the calcium oxide and carbon dioxide, and the carbon dioxide will escape from the container. The reaction will complete because the reverse reaction cannot occur in the absence of the carbon dioxide. This system is the non-equilibrium system where the reaction is the irreversible reaction. If the calcium carbonate is placed in a closed container, the breakdown starts as before, but soon the calcium oxide and the carbon dioxide starts reacting with each other and starts forming the calcium carbonate. When the rate of the reverse reaction occurs as fast as the rate of the forward reaction and the amounts of the calcium carbonate, calcium oxide and also the carbon dioxide no longer change, the system has reached a state of equilibrium. We indicate this condition with a pair of arrows pointing in opposite direction, forward and reverse direction. In contrast to the reaction in an open container just now, equilibrium is reached because all the substances remains in contact with each other. As the calcium carbonate is consumed in the reaction, the rate of the forward reaction will decrease and the calcium oxide and carbon dioxide are formed in the reaction, the rate of the reverse reaction increases. As the two rates becomes equals, an equilibrium state is reached and there is no change in the concentration of the reactants and also product. Law of mass action, also known as the law of chemical equilibrium, will show the relationship between the chemical equation and the expression of the equilibrium constant. The law of mass action states that for a reversible reaction, at equilibrium and a constant temperature, a certain ratio of reactants and product concentration has a constant value K. The value of K is the equilibrium constant. Consider the reaction of A reacted with B in equilibrium with C and D. At equilibrium, K is equals to the concentration of C to the power of its coefficient times with concentration of D to the power of its coefficient over the concentration of A to the power of its coefficient times with concentration of B to the power of its coefficient. The small letter A, B, C, and D here are represent the coefficient of the reaction. So generally, the K expression is the products of a reactants to the power of its coefficient. For a particular system and temperature, the same equilibrium state is attained regardless of how the reaction is run. For example, if you have the reaction of A in equilibrium with B, if you start the reaction with A and there is no B present initially, the concentration of A will decrease with time and the concentration of B will increase with time until it reaches some time where the concentration no longer change, the reaction will achieve equilibrium. If you start the reaction with B and there is no A present initially, the concentration of B will decrease with time and the concentration of A will increase in time until it reach equilibrium. We will obtain this shape of curve when we start the concentration of A. Let's say we have 5 molar here, okay, and then it will reach equilibrium when the concentration is 2 molar, and for B we started with 0 and it will reach equilibrium maybe here in 4 molar. So the curve will intersect like this. The second curve that we might obtain is where the A and B here does not intersect with each other. We will obtain this kind of graph if let's say we start the concentration of A here in 5 molar and it will reach equilibrium here maybe at 3 molars, and the B here we started with 0 molar and it will reach equilibrium here in 2 molar. So these two curves will not intersect with each other. Another curve that we might obtain is like this. So let's say if we start B here in 5 molar and we have A here in 3 molars, B will reach equilibrium when the concentration is, let's say, 7 molar, and A reach equilibrium when the concentration is 2 molar. Or maybe A, we started with 5 molar and it will reach equilibrium at 7 molar, and B started with 3 molars and it decreased until it reached equilibrium at 2 molar. So this type of curve depends on our reaction.